Hi, I am Mladen Čičić from GIPSA Lab, and I'll talk about how we can use connected vehicles to learn traffic models. I'm sure all of you have heard a lot of fantastical stories about how connected and autonomous vehicles are going to change everything, make the traffic flow extremely efficient, and just in general solve all of our traffic problems. But I'm also pretty sure that most of you have been disillusioned, same as myself, by the pace of progress in this field currently. It seems like now that a lot of the hype around autonomous vehicles has died down a bit, the true autonomy still remains far, far beyond reach. In fact, it seems like the current situation where we have a few connected autonomous vehicles, or CAVs, immersed in human-driven traffic will be the case for quite a long time. And this situation is particularly difficult because it's much easier for human drivers to collaborate with other human drivers, and similarly, it's much easier for CAVs to collaborate with other CAVs. However, what we have right now is a mixed traffic of few CAVs and a lot of human drivers, and that is not that easy to handle. However, I think that we would agree also that there is still a huge untapped potential for using connected vehicles for traffic control, with or without autonomy. On one hand, connected vehicles could be used as Lagrangian sensors, that is, sensors that move with the traffic flow and measure it from within. And because there is a lot of data that these vehicles might collect. From one side, they might collect data from their own local sensors, radars, LiDARs, cameras, and so on. But also they might collect data that is communicated to them via V2V, an assortment of collaborative awareness messages or any kind of safety messages as well. On the other hand, the fact that these vehicles are connected means that we could also potentially communicate some control actions to them that they would execute in order to improve the traffic flow in some way. So one of the barriers to using CAVs for these purposes is the lack of established models and the lack of understanding of how exactly they interact with the rest of the traffic. Therefore, the question that we're trying to at least start answering in this work is how can we learn the model of the traffic and the influence that a CAV has on it using only the local traffic measurements. The way we want to deal with this is through using simple targeted experiments to collect the necessary data. We looked at a two-lane road and with a single controlled vehicle, shown in red and followed by the camera here, immersed in human-driven traffic. Sadly, human-driven as in simulated in Sumo, and these vehicles are shown in yellow. At first, the controlled vehicle is moving fast at the speed similar to the rest of the traffic, as you can see right now. And then we slow the controlled vehicle down to a set reference speed and have it affect the surrounding traffic by acting as a moving bottleneck. All the while, the controlled vehicle is detecting, tracking, and collecting the trajectories of all of the nearby vehicles, and we use this data to estimate the steady-state traffic parameters upstream and downstream of the controlled vehicle. Since the controlled vehicle is acting as a moving bottleneck, these should, of course, vary significantly. Then, once we have collected enough measurements for this particular case, we repeat the experiment in potentially different traffic conditions or by setting different reference speeds. And finally, once we're satisfied with the range of different scenarios that we have collected, we use the collected data to build macroscopic traffic models, both for the traffic itself, but also for the influence of that the CAV has on the rest of the traffic. And we're building these macroscopic traffic models using microscopic traffic data. The first problem that we have to deal with has to do with interpreting this microscopic traffic data in a macroscopic framework. On the left side, you can see the trajectories of all of the vehicles in one simulation run. And by the way, throughout the talk, I'll show space on x-axis and time on y-axis. I'm sorry if you prefer it the other way around. And the trajectory of the controlled vehicle is shown in red. You can see that once the controlled vehicle slows down, there seems to be some accumulation of trajectories upstream of it, as we might indeed expect. However, it is very hard to see clearly what's exactly going on, or to quantitatively or macroscopically describe the effects. The traditional way of going from vehicle trajectories to aggregated quantities, such as traffic density, is by discretizing the road into cells and then essentially counting the vehicles inside of each of these cells. On the left, we now show the color-coded traffic density profile with warmer colors representing denser traffic, and we can see that indeed there is some congestion showing up in yellow. The problem with cell-based aggregation is that the picture that we get is typically either too granular or too blurry. On the right, we show an estimate of traffic density at t equals 10 minutes along the dashed white line. And you can see that higher traffic density indeed does correspond to a higher concentration of lines, but it still looks pretty quantized and jittery. And furthermore, since we're now interested in what's happening immediately upstream and immediately downstream of the controlled vehicle, it can be hard to identify which cell or which cells in fact represent what we exactly want to see. Finally, the aggregation method that is best suited for what we're trying to do is using Gaussian kernel estimation. This method gives us a smooth traffic density estimate, which is defined for every position on the road. So how exactly do we go from vehicle trajectories to whatever we want to estimate using Gaussian kernels? We start with the trajectories of the vehicles that the controlled vehicle can detect, and controlled vehicle here is shown in orange. Then we define the traffic state that we want to estimate by indicating the presence of nearby vehicles using a sum of Dirac delta impulses. In this case, if we're interested in average traffic density around the controlled vehicle, we can simply integrate over some range around it, and this essentially counts the number of vehicles that is in its vicinity. And then finally, if we divide this counted number by the width of the zone over which we integrated, this gives us average traffic density. Next, we replace these Dirac deltas with Gaussian kernels and simply let the width of this local zone go to 0. This gives us a Gaussian kernel version of the state that we were estimating. So here the parameter L indicates how local we want this quantity to be, since a higher L will result in a wider area being taken into account. Now, the interesting thing is that we can apply this procedure not only to estimate the traffic density, but also the traffic speed and even some very local quantities, such as the traffic flow that is overtaking the controlled vehicle. In order to learn the macroscopic traffic model, as well as the model of interaction between the CAV and the rest of the traffic, we first need to assume that this model has some specific form. And in this case, we assume that the traffic evolves according to the well-known and loved Lytle-Witham-Richards model. However, here we assume that the flux function of the model is space-dependent, and in particular, we will describe the evolution of traffic away from the CAV using flux function Q0, which is here shown in blue, and the evolution of traffic close to the CAV using the flux function QC, which is here shown in red. Now, as we know, if the traffic flow is high enough, the moving bottleneck will cause the traffic density around it to separate essentially into two distinct zones. Upstream, we will have the situation outlined in red. We will have congestion and higher traffic density. This situation is indicated by traffic density rho minus and traffic flow rho q minus. And then downstream of the moving bottleneck, we have the situation outlined in blue, which is low traffic density free flow and described by rho plus and q plus. Now, the line connecting the points corresponding to these two zones on flux function q0 has the slope which is equal to the speed of the moving bottleneck, and it is tangent to the flux function describing the moving bottleneck, so qc. Because of this, if we're able to estimate the traffic state upstream and downstream, this enables us to essentially identify different parts of the flux function of the overall traffic. Essentially, what we can do is run the experiment multiple times, varying the reference speed of the moving bottleneck and collecting steady state data. So you can see that as the speed of the moving bottleneck decreases, we get additional points. This gives us a simple way to learn a piecewise linear approximation of the flux function by representing it as a convex hull of the collected data points. We can also assume that the jam density is known here denoted by capital rho 0. In a similar way, we can learn the flux function of the moving bottleneck as the lower concave envelope of all of the lines between these identified points on the flux function. And we complete this flux function by again assuming that there is some maximum speed at which the traffic can move, and also that assuming that we know the jam density for this flux function as well, and that its critical density is equal to the critical density of Q0 scaled down by the ratio of their jam density. In reality, however, there will be a lot of noise in these measurements that we will have to deal with. So especially for this case, for the case of the moving bottleneck flux function, it might be beneficial to assume that it takes a triangular form and then to simply fit this breakpoint by least square distance to all of these collected lines. The resulting learned model is defined by these flux functions that are shown. The red and blue points on the big flux function represent the collected steady-state measurements of the traffic state upstream and downstream of the moving bottleneck. And the gray points show the instantaneous measurements of these points. You can see that the flux function of the overall traffic, so the big flux function, seems to be almost triangular, although its slope does decrease as traffic density gets closer to its critical density. Note that the range that we considered for moving bottleneck speeds was not that wide. We considered the moving bottleneck moving from 54 kilometers per hour to 72 kilometers per hour, and this significantly reduces the zone of Q0 that we can identify. We also showed the moving bottleneck flux functions obtained by both of the methods that we proposed. And you can see that they are very close, with one estimated parametrically somewhat better predicting the traffic dynamics. In order to evaluate this learned traffic model, we compared the simulation results with predictions based on our front tracking transition system model. And the prediction model is here only provided with these learned flux functions, the trajectory of the controlled vehicle, and only the average inflow at the start of the road. And as you can see, this model predicts the qualitative behavior of the traffic fairly well, I would say, surprisingly well maybe, and even somewhat far away from the moving bottleneck itself. And in this case, the traffic was fairly heavy, and some congestion did indeed end up accumulating at the moving bottleneck. But even in case of light traffic, the model correctly predicts this little congestion that builds up in this case. Finally, to provide a slightly more quantitative evaluation, we compared the simulated and predicted cumulative flow through a point downstream of the moving bottleneck, which is indicated by the dashed white line. And the model has a relative error of around 5% over a range of different reference speeds and traffic conditions. So to conclude, I hope we have shown that the Gaussian kernel estimation can indeed be used to aggregate vehicle trajectory data, and that it can give us not only the traffic density but also other traffic states, even some more Lagrangian states such as the overtaking flow. And we hope to have also demonstrated that experiments with controlled moving bottlenecks can be designed to learn specific aspects of the dynamics of the traffic, and also including the influence that this moving bottleneck has on the rest of the traffic. Finally, it seems like the front tracking transition system model with learned piecewise linear flux functions can predict the evolution of traffic around a controlled moving bottleneck fairly well. In the future, it would be very interesting to apply the presented methods on real-world data and perhaps even with experiments on public roads. Also, this model is intended to be used for traffic control, in particular Lagrangian traffic control, so we still need to close the loop and design control laws based on it. With that, I'd like to thank you for your attention, and if you have any questions, please don't hesitate to reach out.